Well, thank you for the introduction and thank you for the invitation to give a course in this summer school. As you said, my name is Richard, and my goal here in this talk is to give a gentle introduction to elliptic curves, which are one of the topics of my research. I work in Clermont-Ferrand in France, and I study number theory, but more specifically elliptic curves. Right, so let's go. So I'm going to start by describing two problems, which you can find in a very old book published in the 1920s by Henry Dewdney, this book is called The Canterbury Problems, Amusements in Mathematics. It's a small book with tons of sort of recreational mathematics problems. Okay, I should say right from the beginning, if I go too fast or if I go too slow, you should interrupt me. And if you have questions as well, you should interrupt me, and I will share this file, those notes with you at the end, right? Okay, so yeah, in this book, there are tons of problems about logic, about geometry, and there are two problems which are a bit different. They are more arithmetic in nature, and there are the following two problems. The first one is called the problem of the silver cubes, and it's about a merchant who has a lot of silver, and for some reason he likes to have his fortune organized into in the form of two silver cubes. And at someday he had 16 cube centimeter of silver, and he has them divided into two cubes. And each of those cubes has side length 2 centimeters. So the total volume is indeed 16 cube centimeters. I should maybe make a small picture. And then at this day, he gains 1 extra cube centimeter of silver by sailing something. Now he wants to sort of melt the whole 70 cube centimeters of silver, and he wants to make up 2 new silver cubes with containing this whole volume of silver, right? And what he wants to know is what dimension he should give to those 2 cubes. And one of the extra requirements that's in the problem is that the length of the side length of those cubes should be rational numbers. Okay, that's the first problem. And the second problem is called the problem of the doctor. As you see, it's a bit similar. So it's about a doctor who has a special drug, and she keeps this drug into spherical bottles. And she has one sphere of the drug, which is a sphere of diameter 1 centimeter, and the other 2 centimeter. And she wants to, oh, it's the wrong pen. She wants to, for some reason, transfer the content of those spheres into 2 new spheres containing the same volume of the drug. And she's asking as well for the dimension, the diameters of those spheres, so that the 2 new spheres contain the whole volume of the drug, and the dimension should be different. And again, the diameters of those spheres should be rational numbers. Okay, so those are 2 of the problems that you can find in this book. And as you can see, they are more difficult than the rest of the problems that are in the book. Okay, so it's quite clear that the 2 problems are sort of related, and I will start by stating them in a more mathematical form. So the first problem about the silver cube, well, we want to find the dimension of the cubes such that the total volume, the sum of the volumes, is 17 cube centimeters. So we are trying to find the side length, which are rational numbers, and we call them x and y. And we want that the total volumes of the cube, so x cubed plus y cubed, equals 17. And for the problem of the doctor, well, similarly, we want to find rational numbers, x and y, such that x cubed plus y cubed equals 9. And in each of these problems, x and y are either the diameter of a sphere or the side length of a cube, so they need to be positive. And in the second problem, we have an extra condition. Remember, the doctor wants to know about the dimension of two spheres, but the dimension should be different from the original dimension of her sphere. So we want x and y to be different from 1 and 2. Okay. And yeah, as I've mentioned, these are hard problems. So if you think about it for some time, you might try and find x and y small, let's say up, well, okay. How would you go about trying to find one solution to this? Well, probably you would use a computer, and among all rational numbers with small denominators, let's say denominators up to 10,000, and then small numerators, x and y have numerators up to 10,000 as well. And then for each of those rational numbers, small rational numbers, you would cube them and then sum their cubes and look if the resulting sum is 17. This is one way of doing this. And if you do this, well, you don't actually find any solution to those problems. The only thing you find, except that, if you do this, you probably will recover the fact that 1 cubed plus 2 cubed is 9. So this is this. But this, of course, isn't a solution because you want x and y to be different from 1 and 2 in the second problem. And the other, let's say, relation that you find is that 18 over 7 cubed plus minus 1 over 7 cubed is equal to 17. So you can find two rational numbers, 18 over 7 and minus 1 over 7, whose cubes sum to 17. But this is not a solution to the first problem because, of course, the second of those rational numbers is not positive. Okay, and yeah, we're going to solve those problems today, and also trying to sort of discuss what those problems have to do with elliptic curves and some of the more sort of how you find those solutions, which are again not things that you can find by a simple computer search with small rational numbers. Okay, so now I've stated the two mathematical versions of those two problems. It's even clearer that there are two examples of a more general question. So we'll pick, here we go. Instead of 9 and 17, there's nothing special about those numbers. We'll pick any integer n, which we assume is at least 3. And we'll try and describe rational numbers, x and y, such that x cubed plus y cubed equals n. So this is sort of a general equation, x and y, and we want to find solutions which are rational numbers. I guess there are plenty of questions that you can ask about this, but problem 1 and problem 2 are about finding positive x and y, which satisfy this equation. So we add one extra condition that x and y should be positive. And I should say that this equation x cubed plus y cubed equals n, it's an example of an elliptic curve. And this is, I will try and explain what's special about those equations. Okay, so during the whole lecture, ENQ, it's the set of solutions we're interested in. So it's a set of rational numbers x and y, such that their cubes sum to n. Okay, and there is one such set for each integer n greater than 3. And there are plenty of questions that you can ask about this set. Is there any solution at all? So is this set, does this set contain any rational numbers at all? And if it does contain some solution, how big is it? Is it a finite set or is it infinite? Does it contain any positive solutions with x and y positive? And plenty other questions, I guess. How big are the elements in there? So we won't be able to discuss all those questions today, but I will try and explain some elements of some of the properties of this set of solutions. And at some point, it will be useful to make some restriction on n. And the most interesting case, so I'm not sure I will use this definition later, but just to be safe, I will state it now. We will assume that n is cube-free. What does cube-free mean? Well, it means that when you write the composition of n as a product of prime factors, well, each prime appears at most twice. So whenever a prime number divides n, well, maybe p divides n, p squared divides n, but p cubed doesn't divide n. This is the sort of restriction we're making. So for instance, 54, it's not a cube-free number because when you write the composition into a product of prime numbers, 54 is 2 times 3 times 3 times 3. 3 appears 3 times, so 54 is not cube 3. There is cube factors in there, 27. On the other hand, 18 is square 3 because 2 appears once in the decomposition and 3 appears just 2 times and not 3, so it's fine. And you can find any other example, 10,290. Well, you can find the decomposition. It's 2 times 3 times 5 times 7, 3 times. And since the prime number 7 appears 3 times, this number 10,290 is not cube-free. Okay, and the most interesting case for this question above is when n is cube-free. Yeah, I'll come back to that maybe later during the talk. Okay, so we'll start not by looking at the set ENQ, but at a slightly bigger set, actually much bigger set. Instead of looking at rational numbers x and y, such that their cubes sum to n, here we'll be looking at ENR, and x and y are now allowed to be real numbers. Okay, so that's a bigger set, right? Because there are more real numbers than there are rational numbers. Why is this interesting to do this? Well, because now ENR is a set of pairs x and y of real numbers. And now you can do geometry because x, y are coordinates of a point in the usual plane of of geometry, right? So one thing we can do is to plot this set ENR And I drew the pictures for you here. So ENR is the curve in red, in blue. No, it's green, sorry. It's the curve in green here. And this is what it looks like. So we can do a few remarks on this picture. First of all, yeah, as I've mentioned, ENR is a curve, what we would like to call a curve in R2, so in the geometric plane. And the name curve here justifies part of the name of the equation. I said that this equation x cubed plus y cubed equals n. I mentioned it's called an elliptic curve. Well, this is it's called a curve because, well, the picture looks like a curve. Okay, and the name elliptic is slightly more difficult to explain, but yeah. Okay. The second remark I want to make about the picture is that ENR, you see, it's very smooth. It doesn't have any corners or any peaks or anything. It's very smooth. Also, the curve ENR has a symmetry with respect to the curve, to the line y equals x. Okay, so which means that if you have a solution xy, then yx is also, if you have a point xy, then the point yx is also on the curve. Okay, but this was already something we could maybe expect, because in the original equation, the roles of x and y are the same. So if you exchange x and y, then you end up with another solution to your equation. Okay. And then one thing which maybe wasn't very clear before is the fact that, as you can see, there's another line drawn in on the picture. It's the line y equals minus x, and it's an asymptote to the curve. So if you've never heard of this, it means that as y grows, so as you go north on the picture, I guess northwest, then the curve, the green curve, grows closer and closer to this gray line, y equals minus x. And similarly, when x grows, so when you go southeast on the picture, then the green curve grows closer and closer to the gray line. Okay, and this is what's called an asymptote. Okay. Okay, so this is sort of a basic geometric set of remarks about the curve we're looking at. Okay, we're going to use this in two ways. First of all, now we have a new language to describe our problems. So ENR is this set of solutions x and y with real numbers x and y, whose cubes sum to n. And as I've already mentioned, a point on the curve corresponds to its coordinates x, y, and the coordinates x and y are a solution to our problem. So we can talk, and this is the same thing for this point P on the curve with coordinates x and y. I will call it a point, but it corresponds to a solution xy to the equation x cubed plus y cubed equals n. Okay, so in the rest of the lecture, I will probably use these two words interchangeably, solution to the equation and a point on the curve. Right? Are you convinced? It's the same thing. It's just 2 points of view on the same question. And also the set we're interested in, this ENQ, as I mentioned, is a subset of this bigger set ENR. And how do we recover it? Well, it's the set of points x, y in ENR, so the set of points on the curve, such that both the x coordinate and the y coordinates are rational numbers. Okay, so you don't look at all the points on the curve, you just look at those such that x and y are rational numbers. Okay, and this sort of gives you ENQ, it's a subset, and then that's probably, it's not very smooth curves because it doesn't make sense for rational numbers. Okay, so this is the first thing, 2 points of view, either the geometric point of view with points on the curve or the sort of more algebraic point of view, solutions to an equation. And the important thing about this is the following construction. At first, it probably won't make sense, but you'll see where this is going. So assume we have two solutions, x1, y1, and x2, y2. So what this means is that x1 cubed plus y1 cubed equals n, and x2 cubed plus y2 cubed equals n. So we have two solutions to the equation x cubed plus y cubed equals n. And as we just said, we can view them as 2 points P and Q on the green curve. Okay. Now we're going to do a bit of a strange thing, which is we're going to draw the line that joins P and Q. And the picture looks like this. Draw the line joining P and Q. And the interesting remark about this is that it seems that this curve, this line, the gray line here, well, it intersects the green curve at P, of course, at Q, of course, but also there seems to be a third intersection point here. This is what the next slide is about, is that this gray line intersects the curve in a third point, I. But now this point, I, has coordinates x3, y3, say, and the point I is on the green line, is on the green curve. So it means that x3 cubed plus y3 cubed equals n. Oops. So if we know two solutions, x1, y1, and x2, y2, then it seems that we have constructed a third solution, a new solution. And I'm going to prove this for you right now, that we have indeed a new solution. And something stronger, actually. Okay, so how does the proof work? Well, goes like this. So we start with our 2 points P and Q. Their coordinates x1, y1, and x2, y2 are the rational numbers. And let's review what we've just did. We drew the line which joins P and Q, the gray line. And it's a line in the plane, so you can certainly write down its equation. This line has a slope. The slope is called A, and it has, I'm not sure about the name of this other parameter, but you can find A and B such that the line is given by y equals ax plus b, right? Doesn't sound very surprising. And also, well, you know that this line goes through P and Q, and you have 2 points on this line, so you can certainly find formulas for this A and this B in terms of x1, y1, x2, y2. And if you do this, then you realize that A and B have to be rational numbers. Okay. And what we're going to do is to try to find, first, we're trying to find x coordinates. So those are those numbers here. X coordinates for the points which belong to both the green curve and the gray line. So to do so, well, we're looking for elements, pairs x and y, who satisfy both the original equation x cubed plus y cubed equals n and the equation of the line. So we substitute this equation for the line into the original equation, and it looks like this. Then you expand this and you sort of gather things around. And I'm not going to do this, but we can do a bit of a lot of remarks about this. First of all, the equation that you get is a cubic equation in x, all right? Probably has some x cube in there. And the coefficient of this equation, when you write this, you expand this, the coefficients are products and sums of a and b's, and a squared, b squared maybe, and b cubed, and n. So all the coefficients are rational. So you have a cubic equation in x, which has rational coefficients. So at first it doesn't say much, because there's no reason why the solutions to this equation should be rational numbers. Okay, think of, I guess, x cubed minus 2 equals 0. It's a cubic equation in x with coefficients which are rational, just have 1 and 2. And one solution of this equation is x cubed is cube root of 2, but this is not a rational number. But here the situation is slightly different, because we know that P and Q are both on the line and on the green curve, which means that their x coordinates, which I called x1 and x2, they are two rational solutions of this equation x cubed plus ax plus b cubed equals n. And this is interesting because there is a thing for polynomial equations that there is a relation between their solutions, their roots, and their coefficients. So about sort of sums of roots give you a coefficient, products of roots give you a coefficient, etc. And if you have a cubic equation where with two known solutions which are rational, then the third solution exists and is a rational number. This is here. The equation has a third solution, x3, and x3 is a rational number. So in terms of, on the picture, this would be x2, this would be x1, and this would be x3. And if x1 and x2 are rational number, then this x3 is also a rational number. And once we have x, then we can set y3 is equal to ax3 plus b. And then what we get is a new point, x3, y3, which lies on the line, of course. It also lies on the curve, the green curve. And it has rational coefficients. So what we've done in terms of the problem of finding rational solutions to the equation x cubed plus y cubed equals n. This is when we have two solutions p and q, then we can create a third solution I. Okay, so I should say that I cheated a bit here because this process, which I've just described, actually sometimes fails to work. Sometimes there's just not any third point. So maybe it's clear here. You see here, when you expand this, the term with x cubed, the coefficient in front of x cubed is 1 minus a cubed. And then there are terms with x2 and lower terms. But sometimes a cubed equals 1. So then this first term just doesn't exist. So it's not a cubic equation anymore, but a quadratic equation in x. And then the whole thing just fails. And this happens exactly when a equals -1, which you can see on the picture here. This happens when the slope of the gray line is equal to -1. And as you can see on the picture, this exactly means that the line joining P and Q is parallel to the asymptote y equals -x. And then if this is the case, well, maybe it's not very clear on the picture, but it seems unlikely that this line joining P and Q, it seems unlikely that it will ever cross the green curve at any other point than P and Q. So this is a bit annoying because it's going to create a lot of special cases, and we don't want special cases. So it's just going to solve the problem by creating a new point, which is called a point at infinity. So if you know about projective geometry, then this is exactly a point at infinity. And if you don't know about projective geometry, then I'm trying to explain how this works. We're just going to add one extra point. It's called, we'll call it O, this point. It's not an actual point on the plane R2. It's a point that lives, if you will, it lives at infinity in this northeast, northwest direction, and also is somewhere southeast, right? Okay, it behaves in a bit of a weird way, but you can think of it as an extra point which lives somewhere, which is not exactly on the picture. But how would you describe a point in the plane? Well, you can describe a point in the plane by saying, by telling me about what lines go through it. Okay, if you want to describe the point P here, then you can give me the collection of lines that intersect at P. And similarly, we can describe the point at infinity by saying that the lines that go through this point are exactly the lines of slope -1. So all those lines of slope -1, they intersect at O. So it looks like this, if you want, looks a bit like this. The lines sort of bend toward the point O. It's not very precise. So that's a way of seeing this. So again, let's imagine that we virtually add one artificial point to the picture. The point cannot be seen here, but it's infinitely far in either the northwest of south or southeast direction. And we're just saying that any of those lines of slope -1, they intersect this point O. Okay, and if that's the case, well, we're just going to say that P and Q are two points on the line, and then the third point of intersection between the gray line and the green curve, the third point will be O. Okay. So with this construction, what we just did is that if we have 2 points P and Q, which are correspond to solutions to the equation ENQ, then, well, there is a third point, I. This point is either in ENQ, or it's one of this artificial point O. And in all cases, this point has the property, the point I has the property that P, Q, and I, they all lie on the same line. Okay, the line that joins P and Q. And this can be done very explicitly, actually. So if you take n equals 1729, and I can give you two solutions to this, to the equation x cubed plus y cubed equals n. You can see that 1 cubed plus 12 cubed is 1729. And also that 9 cubed plus 10 cubed is 1729. So this is sort of the world of arithmetic. And then with geometry, you can say that the point P with coordinates 1 and 12, and the point Q with coordinate 9 and 10, they are both points in this set ENQ, where n is 1729. And so you have 2 points. You can compute the line, the equation of the line that joins them. And you then get this cubic equation in X that I've mentioned. And then you can solve this equation, maybe using a calculator. And then you find coordinates for this point I. You find that minus 27 third and 46 third also lies on this curve, which means that you get a new relation. It says that minus 27 third cubed plus 46 over 3 cubed is 1729. I think there's a mistake here because 17 over 3, 27 over 3 should be simplified. Yeah, I must have made a mistake somewhere. But the point is, even if the coordinates are not right, I hope you're convinced that this is something that is doable. I give you 2 points. You can compute the lines that joins them and compute the intersection with the curve, the green curve that we had on the picture. So this is a very sort of it's a bit of magic, right? If you know 2 solutions to the equation, then you can construct a third one. Sometimes it's not an actual solution at this weird point at infinity that doesn't really exist and that we don't really care about. But generally speaking, this works well. What if, so this is all very interesting, but if we think of the 2 problems, the problem with the silver cubes and the problem with the doctor, this is not very interesting because in each case we don't, well, for this to work, we need 2 solutions. And in the problem is at the beginning, we don't know 2 solutions, we know just 1. So how are we going to work around this issue? And the trick, one trick at least, is, well, now we started with just 1 point P with coordinates x1, y1. There's coordinate coordinates are rational numbers. And instead of drawing the line joining P to Q, here we're just going to draw the tangent line to ENR at P. So we have just 1 point, and we draw the tangent line. And sort of the same process will give you another point I. Okay, you have a line. You can write down its equation. The coefficients of the lines are rational numbers. You substitute for y in the original equation x cubed plus y cubed equals n. You again obtain a cubic equation in x. It still has rational coefficients. And the trick that we used before, if I have a cubic equation with 2 rational solutions, then it has a third solution, which is also rational. This time we only know one solution, but it counts as two solutions. So we can use the same trick. There is a third solution, x3, which is rational. Yeah, and as before in this, even if we have only one point P to start with, then we obtain a third point I with coordinates x3, y3, which are rational numbers. And again, this fails if the tangent line has slope -1. And in this case, we use the same trick as before. We define the third intersection point to be I. I equals O, the point at infinity. Okay. So one example of this process is this one. So again, the way I describe this with words, I hope it's clear that this is a problem that can be, this is a process that can be dealt with explicitly. So we start with n equals 17. So it's the problem, the setting of problem 1. We're looking for rational numbers x and y such that x cubed plus y cubed equals 17. Okay. And we found, or you can find if you try by using a computer search, that 18/7 cubed plus -1/7 cubed is 17. So we have, if we look at the point P with coordinates 18/7 -1/7, then it's a point on the curve E17R, or E17Q actually. And I have the equation for the curve E17R. I have the coordinates of P, so I can compute the equation of the tangent line to the curve at P, and that's this equation. And then we do the steps I described explicitly. We substitute y in the original equation, and then we find a cubic equation in x, which is a huge coefficient, so 49 squared times 18 squared times 17 squared. Which is a bit scary, but if you use a computer, then it solves pretty easily, and you find that this huge equation factors is this, where so we find it's very explicit here. We know that x equals 18/7 is a solution. It actually appears twice. And then we find a new solution, which is this rational number here. And this means that the point I with coordinates given by this, those huge fractions, this point lies on the curve E17Q. In other words, what this shows is that we have this relation, 104,940 divided by 440,000, etc., cubed plus the other coordinate cubed is equal to 17. And the nice thing about this, this point I that we have just created, is that the first coordinate x and the second coordinate y, they are both positive, which means that this, this solution here is a solution to problem 1. I have found for you two rational numbers which are both positive and whose cubes sum to 17. And the fun thing about this, I guess, is if you find this book by Dewdney and you find the original problem with the cubes, then you can go to the end of the book where he gives solutions to problems. And he just gives this solution here. and he simply gives the solution and doesn't explain how to find it, which is a bit weird, because it's actually very difficult to find this solution by trial and error. Again, if you want to look with a computer for small solutions, you look for all rational numbers with all small denominators and small numerators. You just cube them and sum the cubes and try and see if the sum of the cubes is equal to 17 or not. Well, you have to go pretty far to find this solution. You have to go to 1400. 40,000 actually, as a denominator and more. Yeah, and again, the book by Dewdney was published in the 1920s, where when computers and calculators were not easily available. So there's the secret trick at the time to solve this first problem, and actually the second problem as well, was to know about this process of creating new solutions on elliptic curves when you know one solution. Okay. So this process of creating new solutions from old ones is called the chord and tangent process. So if you have two solutions, well, what we did was draw the line joining them. And this is called drawing the chord joining P and Q. And if we have one solution P, then we drew the tangent line. So the process that we use to create new solutions is called the chord and tangent process. And what we did was build a point, I, which it was either in the set E and Q, so an actual point xy with coordinates x and y, which are rational numbers, or this virtual point at infinity, which we call O. Okay, and by the symmetry of the curve, the green curve, the point I, if we reflect it with respect to the line y equals x, the new point, the reflected point, also belongs to the curve, the green curve. And we are going to denote this reflected point P plus Q, where the plus has a circle around it to remember that it's a slightly weird plus. And if we have a point P with coordinate x and y, I'm going to denote by minus P the point yx, which corresponds to the reflected point with respect to this symmetry. You exchange x and y. And it's, again, the minus sign has a circle around it to remember that it's a slightly weird minus operation. And this allows to give cool statements, which I will try to describe in elementary terms. So we started from this set x, y in Q squared, such that the sum of their cubes is equal to n. We've added the point at infinity O to this set. And we have defined an operation plus, and this is on the previous slide, plus with a circle around it. And in fancy terms, what we could show is that this new set with this operation is an abelian group. I'm not sure if you know about groups, but so I'm going to describe in words what it means. It means four things. First of all, if you have any point on the curve and any point plus with a circle, the point at infinity O, then P plus O is equal to P. And O plus P is equal to P. which means that plus with a circle, if you add O to any point, then it's just as if you didn't add anything. And then for any point P, if you add, in terms of, well, plus with a circle, if you add P to the point minus P with a circle, then what you get is the point O. Okay, and if you have 2 points P and Q, then adding with respect to this operation plus with a circle, adding P and Q is the same as adding Q and P. So if you just look at the first 3 operation and think of what you know about integers, think about integers, but don't think about multiplication. Just think integers with the operation plus, with just the addition, the thing you learn in school. Then integers, if they have an element, so if you have an integer x, for any integer x, x plus 0 is the same as 0 plus x is the same as x. If you have an integer x, then x plus minus x is equal to 0. And if you have integers x and y, then x plus y equals y plus x. Which means that this, so this is this set, E and Q together with this point O, with the operation plus with a circle. The properties in terms of algebra are similar to the integers with, if you consider them with the operation plus, with integers with addition. Okay, and the point O in this set, in the blue set on the left, behaves as you can see. P plus O is equal to P. This reminds us of the fact that x plus 0 is equal to x. So O is sort of plays the role of 0 in this analogy. Yeah, so this is a bit of algebra. There is a fourth point, which I won't go into too much detail here. But the whole point of this slide is to tell you that we started with a simple, or at least an arithmetic problem, try and find solutions to an equation, and sometimes, most of the time, there is no structure to the set of solutions. Maybe you get 1 solution, 2 solutions, but here we get much more structured set of solutions, because we can define an operation on them plus with a circle, and this operation allows you to create new solutions from old ones, and the rules for this operation plus with a circle, they are similar to the rules that you learned in school for adding integers or subtracting integers. So this is very cool, and this is one of the reasons why ellipticals are studied so much. It's because the set of solutions is not just any random arbitrary set, because of this extra structure, this magic operation that you get, in which I've spent some time describing, this plus with a circle. Okay. Maybe I should say that the process that we use to define this operation plus with a circle, I described it in words, but you can make it entirely explicit in terms of formulas, which are scary and you don't have to write them down. I just want to say that those formulas, they exist. So if you have 2 points, you know the coordinates of those points. Then going through the slides once more and sort of writing down what I said in words. If you write the formulas down, then you can find the formulas here for P plus with a circle Q and P plus with a circle P, where P and Q are distinct, and this is when the case where P equals Q. There are formulas for those, for the coordinates of this point. Again, it's not important what the formula is. What's important is that the formula exists, and you can sort of plug this into a computer and work with this pretty explicitly. Okay. Here, so let's go back to the original problems. So the first problem, the problem of the silver cubes, we were asking about the side length of two cubes whose total volume should be 17 cube centimeters. And we've already solved the problem a couple of slides earlier. And we did this by starting from the original solution that we knew. And we computed that P plus with a circle P has positive and rational coordinates. I didn't copy it again because it was a big fraction. Remember, we had huge coordinates. And we can now solve the second problem. We want to find x and y positive rational numbers such that x cubed plus y cubed equals 9. And we know one solution. We know that 2 cubed is 8 plus 1 cubed, which is 1. The sum equals 9. And this is a solution that we will call P. And using the formulas that I just wrote down, I found this set of solutions. So we compute first P plus with a circle. And we find that this has coordinates minus 17 over 7, 20 over 7. Okay, which is a new solution to the problem. But the first coordinate is not positive, which is not what we're looking for. Okay, so why not try P plus P plus P, 3 times P? Well, again, the coordinates don't seem to be both positive. The second one is negative. Okay, so let's try P plus P plus P plus P 4 times. And then again, you find that the first coordinate is negative. So not a solution to the problem. And then you try 5 times P, and then you have this, and then you're slightly tired, but then you try 6 times P. So P plus P plus P plus P plus P plus P. And then you find that this solution has coordinates given by those fractions here, and they are both positive. And then you can check on a computer that the cubes of those two those two coordinates, they are equal to 9. The sum is equal to 9. Okay, so maybe I should pause here. This is this solution here. So this is a solution to the problem of the doctor, because we have found 2 rational numbers whose cubes sum to 9. And those are huge fractions, right? They have 12 digits in the numerator, 12 digits in the denominator. But this is the smallest solution to the problem. This is the smallest solution that you can ever find. And again, in the book by Dewdney, you go to the end of the book and there are solutions to the problem, and he just states, oh, well, here's the solution. And he just doesn't explain how to find it. If you can't, you can't find this by looking at random with a computer, right? You look for, again, small solutions. You can never find this, I don't think. So this is maybe a bit of, let me just state that. So what I wrote down here is the A solution to the problem. It's the smallest one. Okay, and that's easy. I give you the 2 fractions here. And then using a calculator, you compute their cubes and you sum them, and it's easy to check that this is indeed a solution, that the cubes sum to 9. You can check. If I give you the solution, you can check it's an actual solution. But finding this solution is very hard, unless you know this trick with adding points. So this is one of the reasons why elliptic curves are used in cryptography, is that well, it's a typical problem in crypto. I have given a solution, it's easy to check that it's actually a solution, but finding the solution is very hard. So imagine that the message, the secret message is, say, the first coordinate, the numerator of the first coordinate, then it's difficult to find it. On the other hand, it's easy to decrypt if you already know the solution. The point is, it's difficult to reverse engineer, right? Anyway, and also I should say something, is that if you look at those two in terms of arithmetic, if you look at those two coordinates here, as rational numbers, they are very complicated because the numerators and the denominators, they all have about 12 digits. So they are hard to find. But if you look at this, if you compute this, an approximation of this fraction with a computer, then as you can see, this is probably close to 1,3 or something. And this is probably close to 1.9 something. So as real numbers, those two coordinates are not very big. They are not very difficult to understand, right? Maybe between 1 and 2. But as rational numbers, they are very big. Yeah, this is an interesting topic in arithmetic. What is the size of, what are the size of solutions, not just as real numbers, because we don't really care about the size as a real number. We want to know how complicated it is to write down the actual fractions, so how many digits there are in numerators and denominators. So this is another topic. Okay, so maybe a summary of what we did this far. So we are trying to understand solutions of certain equations, x cubed plus y cubed equal n. And here we're just looking at x and y. We just want x and y to be rational solutions. We don't want real solutions, okay? And we defined a set. And with a combination of geometry, USIIM algebra, and etc., we've seen that the set of solutions, if we add one extra point, then it has some extra structure. There's an operation called plus with a circle, which allows us to build new solutions from old ones. And that this operation is described in terms of algebraic formulas, which we can plug into a computer and try to find new points explicitly with actual coordinates, as we've just seen on the previous slides. And this is how we solved our two problems. Okay, and as I mentioned at the beginning, there is a huge number of questions that you can ask about those equations in terms of number theory, in terms of arithmetic. But I just want to discuss one further topic about this. It's the question of the number of solutions in ENQ. So this is the following theorem. So I just used the same notations before. And the theorem says that if the set of solutions, if it is not empty, then the set of solution is infinite. So which means that if I give you an integer n, then there's there are two cases. The first one is, well, maybe the set of solutions is empty, which means there are no x and y rational numbers such that x cubed plus y cubed is equal to n. There are no solutions at all. And the second case, well, if it's not empty, this set, then it is infinite. It contains infinitely many x and y's, which are solutions. Again, there is another question that you can ask, which I won't talk about today, but I mentioned that this theorem is very good, but it doesn't tell you anything. If I tell you, say, n equals 55 or 54, which case are we in? If n is 54, is the set empty or is it infinite? And the answer is, I don't know. It's a very difficult problem. There's been a lot of work on this question about deciding whether we're in case I or case 2I. This is a difficult question. And there are a lot of results of the type, well, if n is of a special form, then we're in case in the first case or the second case. So here's an example due to Sache in the 1980s. If n is 2 times a prime number and the prime is congruent to mod 9, then the set of solutions is infinite. But yeah, it's still an open question. And I'm not sure I have time to prove this theorem, but I can tell you a bit about what goes into the proof. Yeah, okay, so maybe I will have to skip some of the details here. So what we want to show is that if the set of solution is not empty, then there are infinitely many solutions. And we use what we did before. We use this operation plus, and we use the geometric point of view on the question. So if we have a solution x1, y1, we call it a point, P1, and we compute the point P2, which is P1 plus P1, plus with a circle. And then we set P3 is P2 plus P2, and we go on by recursion. If we have computed P sub k for an integer k, then we compute P sub k plus P sub k, and we call this point Pk plus 1. And if you work out the details, you can check that the point P sub k is an actual point on ENQ. I cheat a bit here because this point, it's the sum of 2 points, sum with a circle, but it actually could be the point at infinity. It could equal O. And the point here is that it doesn't equal O. It's not the point at infinity. It's a real point. So pk has coordinates xk, yk, let's say. And the idea to show the theorem, we want to show that this set is infinite. We knew one point, P1, in there. And we've created a sequence of points, P1, P2, P3, etc. And if we show that the sequence P1, P2, P3, P4, etc., if we show that it does not repeat, then this is a sequence of infinitely many different points. So we have produced, we sort of explicitly infinitely many points in the set. So infinitely many solutions to the equation. So this is it suffices to show that this sequence does not repeat. but it's a sequence of points in the plane, in the geometry, the geometric plane. So it's difficult to show that it does not repeat. And the trick to show that it doesn't repeat is to use the following construction. So for each point, it has coordinate xk and yk, and the coordinates are rational numbers. So we can write them in reduced form. They are just fractions. So we write xk in the form a over c, where a and c are integers, which are co-prime. So just meaning I write xk as a reduced fraction. And then I do the same for yk. And if I do this, I will realize that the denominator of yk is the same as the denominator of xk. And a, b, and c, they are integers and they are co-prime, which means that they have no common prime factors. And ck will be called the denominator of the solution pk, because it's the ck is the common denominator of both coordinates of pk. Okay, and I will set, this is definition, I will call denominator of pk, it's the absolute value of ck, so it's the size of ck. And to show that remember, we want to show that the sequence of points p1, p2, p3, etc. does not repeat. And we can do this by showing that the sequence of denominators is increasing. Okay, this is a simpler problem because this is a positive integer. This is a sequence of positive integers. Compared to this sequence here, it's a sequence of points, which is difficult to understand. But this new sequence is a sequence of integers, and we'll show that it's increasing. Okay, and it's true, right? If the denominator of P2 is strictly larger than the denominator of P1, then P2 cannot equal P1 because the denominators do not match. And then if the denominator of P3 is larger than the denominator of P2, then P2 and P3 do not match. They cannot equal to each other because the denominator of P3 is strictly larger than the denominator of P2, which is itself strictly larger than the denominator of P1. So P3 is also not equal to P1, etc., etc. The point is, at each step, P1, P2, P2, P3, etc., we increase the size of the denominator. And this is something which maybe you can believe, because in a slide earlier, I computed multiples of a point here. This was the case where n was 9. As we started from a point p, which had denominator 1, and then we computed p plus p. This is denominator 7. And then we computed p plus p plus p plus p at denominator 438. And then 4 times p was with denominators 19,000 something. And then, as you can see, the denominator does increase when you look at a point plus a point, 3 times this point, etc., etc. So this is how the proof of the theorem that says that if you have one solution, then you have infinitely many. This is how the proof works. You show that the sequence of denominators is strictly increasing, which, again, if you do this computation on a computer or on a calculator, it's very clear that this is what's happening. Work out some examples and you will realize that not only does the denominator increase, it increases very fast in this sequence. Okay, so I will skip the details of the proof. It's a lot of arithmetic. I will share the slides with you, and if you have time or if you're interested, you can look at the details. So one further thing, which is a very important theorem for elliptic curves. As I've just seen, as I just said, we know something about the set of solutions. The set of solution is either empty or infinite. And we have added a point O, which is a virtual point. And so what the previous theorem says is that this set is either only just a point at infinity, or it's an infinite set. So this is just one point, or infinitely many points. But as you may know, there are different types of infinite sets. There are sets that are slightly infinite, and there are sets that are huge, like the set of integers and the set of real numbers. One of them is countable, the other is uncountable. And the theorem, which is on this slide, says that this set is can be infinite, but it's sort of, you can understand it in a finite number of steps. Okay, which means what does the theorem? So this theorem is due to Mordell and Weil. I just stated a special case, which is what we are interested in here. And it says that there exists a finite number of points in the set E and Q. So let's call them P1 up to PR. So there are solutions P1, P2 up to PR with the following property. Any solution, any point P in E and Q can be obtained as a sum and as an addition and subtraction of those points P1 and PR. So any point P, you can write it as, for instance, P1 plus P1 minus P2 minus P3 minus P3 plus P4 up to, I don't know, 5 PR, okay? So even if there are infinitely many solutions, they can all be constructed from a finite number of solutions. So maybe I should have written this in this way. I'm not sure what's the clearest way to state this. All solutions can be constructed from finitely many, well, from P1 up to PR by the operation plus and minus. Okay, so in fancy words, the one-line way of stating this theorem is that the abelian group that we've constructed, we've discussed earlier today, is finitely generated. Okay, so in examples, it's pretty clear what this theorem means. So for n equals 9, it's difficult to show, but you can do it, that all points, all solutions to the equation E9Q, they are multiples of this original solution P1. So it means that all the solutions are P1, P1 plus P1, P1 plus P1 plus P1, and then there is minus P1, minus P1, minus P1, etc., etc. Okay? So there are multiples of this initial, this generating solution. Okay, you have one solution, and using this, you can write all the sums of this solution with itself, and all the subtraction of the solution with itself. Okay, and the same phenomenon appears for an n equals 17. We have one solution, P1, which you can use to deduce all the others. Again, for n equals 7, so this I didn't discuss, but you can see that 2 cubed plus minus 1 cubed is 1 minus 1, is 8 minus 1. This is actually 7. And all the solutions in rational numbers to this equation, x cubed plus y cubed equals 7, you can deduce them from this original P1. But this is not in general true that you only need one solution to create them all. And this is a case that I mentioned earlier in the talk. When n equals 1729, you need at least 2 solutions to 2 generators, because the solution P1 with coordinates 1 and 12, and the solution P2 with coordinate 9 and 10, well, you cannot write P1 as P2 plus P2 plus P2 a certain number of times. And conversely, you cannot write P2 as a multiple of P1. So they are not multiples of each other, which means that there are some solutions which are a sum of P1 and P2, and you actually need the 2 generators P1 and P2. Right, so this is called the Mordevai theorem. It says that maybe the set of solutions is infinite, but if you find those small solutions, the generating solutions P1 up to PR, then you can reconstruct all solutions. This is, yeah. And just to conclude, some sort of some things to think about, which I'll just state as facts, and you can think about it. Those are sort of exercises which are doable, I guess, but they are maybe a bit hard. But there are 3 facts. If n is cube-free, I've introduced this notation before, and then if you have a point P, if you have a solution in E and Q, and if you have any integer m, and you look at the point P plus P plus P plus P plus P m times, then this point is not equal to O. So m times P doesn't equal O. So in fancy language, if you know about groups, this is saying that this group, which we've discussed a lot today, this group doesn't have any torsion. And you can use the theorem about ENQ being infinite. And the way we prove this is by showing that the denominator increases. And being a bit more precise about how the denominator grows, you can use this to show that this statement, right? An easier exercise, which is fun. Instead of, we've been talking a lot about rational solution x, y to a given equation. But if you like number theory, maybe, or arithmetic, then maybe you want more strict condition on the solutions. So you look at x and y being integers, and such that x cubed plus y cubed equals n. And we've seen that ENQ, if it's not empty, is infinite. So there are infinitely many solutions in rational numbers. But when you restrict to integer solutions, then what you get is a finite set. And yeah, again, I will leave this as an exercise, but a hint is that you can factor x cubed plus y cubed as a product of 2 integers. Then think about what it means for n. N is an integer as well. If it factors, then you can say something about the divisors, for instance. And something which really ties up with what we've discussed today is the following fact. If there are infinitely many solutions in E and Q, then there are infinitely many pairs xy with x cubed plus y cubed equals n and x and y positive. which means that in the original problem with 9 and 17, and actually for any n such that there are infinitely many solutions, then well, there are infinitely many positive solutions with positive x and y. And the point is, if you have a point P, if you have a solution P, then using this operation plus that we discussed and adding P to itself sufficiently many times, then you end up with points that are that have positive coordinates. Yeah. And in the last 5 minutes, I should discuss more general elliptic curves. So as I've mentioned, the equations that we've been studying, they are examples of elliptic curves. So the equations were x cubed plus y cubed equals n. And one way of defining elliptic curves is the following. An elliptic curve or a cube, it's an equation as well. It's an equation of the form y squared equals x cubed plus ax plus b. And a and b are two parameters, which are rational numbers. And you can basically choose any a and b, but we want to assume that 4a cubed plus 27b squared is not 0. And yeah, this is a special condition for elliptic curves. The previous examples, this x cubed plus y cubed equals n, they don't really look like this type of equation. They are elliptic curves in disguise, if you want. There is a change of variables, which I wrote down here, which will transform this equation into an equation of the form y squared is x cubed minus 432n squared, which does look like the equation of an elliptic curve. And this transformation is not a bijection exactly, but almost a bijection. So you can transform solutions into one another. Okay, and this, so the elliptic curves, this is sort of, you have parameters a and b, they're rational numbers, you're basically free to choose them. So this is just not one equation, but a family of equations, and they have been studied a lot. And the point is, as I've tried to explain today, and this is some of the things that actually generalize, is that this is not just an equation with solutions that come at random. There's a lot of structure for those elliptic curves. There's things you can say from the arithmetic point of view. You can say, yeah. There's an algebraic point of view. You can add points on elliptic curves. You can add solutions. And there's also a geometric structure because, well, just as we did today, you can draw pictures. You have this chord and tangent process, which you use to construct new solutions. And yeah, there's a lot of structure, which is why those elliptic curves appear in a lot of topics in number theory, and is also why they are used in cryptography and other more concrete questions. It's because there's a lot you can say about their arithmetic. And some of the things I've mentioned today are still true for a more general elliptic curve. So what I call this group structure, that you can add points on elliptic curve, this is still true for a general elliptic curve. The fact that the set of solutions which you you can build it from finitely many solutions. So this is the finitely generated statement. And also that you have only finitely many solutions in integers. This is still true. This is just sort of an opening to further topics if you're interested. And if you're interested in elliptic curves, there's two books I recommend that you read or take a look at. There's a book by Joe Silverman and John Tate, which is called Rational Points on Elliptic Curve. And it's a very nice introduction to sort of the next step to what I've discussed today. They introduce in a very nice and well-written manner, they introduce elliptic curves and some of the questions which we've discussed today, solutions to some elliptic curves, solutions in rational numbers. And Joe Silverman has written 2 further books on elliptic curves, which are much more difficult, but they're next step if you're interested in this topic. And I should also recommend a book by Mark Hindry. It's called Arithmetic, and chapter 4 in there contains a lot about elliptic curves. And the book more generally contains a lot of things about arithmetics in general. And yeah, might be interested, if you're interested in number theory and all those topics, then you might consider looking at this book. I think both books are published by Springer, but yeah, this is 2 suggestions for further reading. And I guess I'm done. Thank you very much for your attention. If you have any questions, I can answer them now. And I've just seen that I haven't looked at the chat where there were a lot of questions. Okay, I will get them.
Dr. Richard, there are questions in the column chat.
Yeah.
Maybe you can answer it directly.
Yeah. So there is the first question, which is, okay. If we know one solution, x1, y1, instead of drawing the tangent line, could we also take y1, x1 as another solution? Right. This is true. If we know that x1, y1 is a solution, so this is a picture here, I can do the symmetric here and transform it into y1, x1. This is another solution. But it's not really different from the first one, because remember what we did later on. We started from a solution P, and with this tangent thing process, we could compute P plus P, P plus P plus P plus P, and we get infinitely many different solutions. So the process that you're suggesting here, which is taking P and exchanging coordinates, well, it's not creating a new solution, because you start from P, you go here, and then if you apply the process again, then you end up where you started. So you get only 2 points, and that you cycle if you repeat the process. So that's why we have to use this more difficult construction with the tangent line here, which I explained here. Why is it important to talk about rational numbers instead of real numbers? Does it have anything to do with crypto? And if we take a real number, would it be useless in crypto? So you can talk about real numbers, real solutions. That's just a different topic, I guess. We look at rational numbers, rational solutions to the equation, because well, it's just a different question you can ask. I like to ask questions about arithmetic, and in arithmetic, you just look at integers or rational numbers. And real numbers, they are useful in this question because we want to draw pictures, and the geometry works well with real numbers. It doesn't work really well with rational numbers. And this is, in that sense, the real numbers are still useful, but we are not interested in solutions in real numbers. And indeed, in cryptography, I don't think real numbers are very useful. The point is that the real number is difficult to work with because there are infinitely many digits, usually infinitely many digits after the comma. And computers which are used in cryptography have only finitely many, can only handle finitely many digits. So you work with approximations which are rational numbers. I'm not an expert, so this is my stupid answer to this question. Then there's another question from the previous slide. I'm not sure what slide is referred to here, but we know that if we have only one solution, x1, y1, we can use the tangent line to get y equals ax plus b. Then why do we get x cubed plus ax plus b cubed equals n? What? Yeah, right. Okay. So I guess this is this slide again. So yeah, what we are doing here is the same as what we did on the previous slide with P and Q, and then we sort of join P and Q by a line and look at the x coordinates of the points which are both on the line and on the curve. Then we write down this equation here, x cubed plus ax plus b cubed equals n. And this is the equation describing the x coordinates of points which are both on the curve and on the line, on the green curve and the gray line. And in the 2 points case, and this is this slide, we have yeah, okay, yeah. We have 3 points in this intersection. So we have 3 x coordinates. Okay, now I haven't drawn the corresponding picture, but think about what happens when P is fixed. You fix the point P, and you move the point Q towards P. So you draw a series of pictures where Q does travels towards P like this. Okay. Okay, now x2, as you do this this process, x2 gets closer to x1. I guess that's pretty clear. What about the line, the gray line? Well, if you remember how we define the tangent is defined by a limiting process with derivatives and stuff. And the line joining P and Q, when Q grows closer and closer to P, the line joining P and Q tends, and in between quotes, this is not very precise, but the line joining P to Q tends towards the tangent line to P, to the curve at P, sorry, tangent to the curve at P. So in this sense, the sort of the tangent process 2 slides ahead is a sort of a limit of the chord process that is on this slide. Okay, and then that's why I said that x1 equals x2 is a sort of a double solution. It's because we think of the tangent process as being a limit of the chord process. So like this would be P, and there's a limit of points Q where we draw the lines joining P and Q, and they slowly tend towards the tangent, and their x coordinates x2 tend towards x1. So this x1, x2, they sort of in the limit, they sort of become equal. Okay, this is sort of a justification of why we say that x1 is a double root. But if you do the computation, then you realize this is true. Okay, then I hope this answers the question. Yeah, okay. Okay, then there are 3 questions. I want to know more about cube numbers and cube free. What kinds of number include in a cube free number? Cubes, there are one set of integers. So they are very far apart. And cube free is sort of the opposite. So 8 is a cube, 7 is not a cube. But you have some numbers that are in between. So 16, for instance, is not a cube. It's not a cube of an integer, but it's 8 times 2, and 8 is a cube. So for some number theory problems, it's important not only that so 8 is 2 cubed, 16 is twice a cube, so not a cube, but not cube free. Because there is a cube factor in there. And for a certain number of problems in arithmetic, it's sometimes it's useful to restrict to numbers that are cube free, because it's a more precise distinction. You have the first distinction, that's cube versus not cube. But yeah, you see 24, for instance, is also 3 times 2 cubed. It's not cube free, but it's not a cube. But 2 appears 3 times in the decomposition. Sometimes this, for some problems, this is too many. Do we have an example of this phenomenon? Let me think. Okay, let's say we have, well, we've already discussed this, 2 cubed plus minus 1 cubed. This is 7. Okay, but from this, I can multiply this by 8 and say that 2 cubed times 2 cubed plus minus 1 cubed times 2 cubed is 7 times 8, which gives me some relation. 4 cubed minus 2 cubed is equal to 56. And the point is that this, so from this solution 2 minus 1, this is a solution to the equation that we've been studying for n equals 7, we get for free almost a solution for n equals 56. But we cheated a bit here because everything in this relation is divisible by 2 and actually by 8. And I guess this is where this distinction cube versus not cube is not enough if you want to do some interesting arithmetic. Because here, the problem is not that 56 is a cube or not. It's just the fact that it's divisible by 8, which is a cube, which is important. And this is, yeah, this sort of construction, okay, I'm just going to multiply everything by 2 cubed or 3 cubed or 27 cubed, I don't know. This is a sort of cheating because it doesn't create actually new solutions. It's just things that you could have deduced from earlier things like we did here. And this is where this distinction is not enough. You actually have to assume that the numbers you're using are cube-free. Yeah. Do I use a software to get solutions of elliptic curves? If yes, what kind of software? I don't actually use software very much. I just, for the computations in preparation of today's talk, I just plugged in the formulas in Mathematica and also Sage Math. But this was just, I'm not very good with computers, so I don't use a lot of software. But if you want to study elliptic curves, I guess the standard software is Sage Math, there's Magma, also Paris GP. Those are 3 things. I'm interested in the operation O plus when E and Q is an abelian group. Is the operation oh, okay, no, it's not a direct sum. Plus with a circle is not direct sum. It's just I could. It's just the notation is similar. I just wanted to make a different notation of plus than plus. P plus Q. P plus Q is not, I guess the point is it's not x1 plus x2, y1 plus y2. This is the distinction I wanted to make, that the operation plus with a circle is not the usual addition of vectors in the plane. Does that clear things up? The operation is not direct sum. Yes. Why we need the condition? Yes, in the definition of an elliptic curve, that's a good question. In the definition, why do we need this condition? This is I guess you've all heard about quadratic equations and computing the discriminant delta, right? This is important to know about roots of quadratic equations. And here, this 4a cubed plus 27b squared is a discriminant, this time for a cubic equation. And it's important because if you draw the picture of what this elliptic curve looks like, it looks like this type of curve. This curve being smooth, having no sort of rough points, is equivalent to having this condition of non-zero discriminant. If this discriminant is 0, the elliptic curve becomes what's called singular. So for instance, it looks like this, or it has sort of a cusp or a node or something. And we want to avoid this. We want the curve to be smooth because we want to be able to draw tangents to this curve at any points. Yes, so it's a smoothness condition. Right, I guess I answered all the questions that there was in the chat. Is there any further questions?
Maybe from the offline participant who want to ask, you can ask the microphone to me. I just talked about the Weyl theorem, the last theorem.
The Monitor theorem, yeah.
Theodore Whale theorem.
I can't hear you very well, actually. Sorry.
Mother whale theorem. Is there any way to get the P1, P2, how to define the P1, P2, and P3?
Excellent question. The answer is no, and it's a big problem. So yeah. So the Monitor theorem tells us that there exists this finite set of points from which you can generate the whole set of solutions. But this is an existence statement. It tells you that the set exists, but it's not an effective statement, which means that the proof of this theorem doesn't give you any recipe to compute P1, P2, PR, and it doesn't even tell you how to compute R. So you're looking for points P1, PR, but you don't know how many, and you don't know how big they are, and yeah, you have to find another way of proving that you've finished the computation, but it's essentially a case-by-case computation, and there is no algorithm at the moment which will do this computation for you. In general, if you have a special case, then you can maybe find out some special relation. So in the examples here, you can actually prove that you find one point and it's enough, but that's not quite easy. But no, yeah, in general, very little is known about R. How many points do you need to generate all solutions? And very little is known about how to compute P1 up to PR, to compute those points.
Thank you. Is there any question from the outside participants? Okay. Yeah, I think that's all. Thank you very much, and let's give him a big applause. Thank you very much, because you are not only sharing about the electrical, but also why is it important in cryptography, especially the kind of structure that will be used. And actually, for the standardization of elliptical cryptography, you can find it in ISO IEC 15946/2017 and the revision 2022. So that's the standardization of elliptical cryptography. And there are some revisions and there are some code that previously will be used, but it's not that secure anymore. So there are some revisions there. But of course, if you want to download the ISO document, you should pay. That's the use of elliptical cryptography. So I think we can give one more applause to Dr. Richard Griffon.
Thank you so much for your attention. I wish you all a nice summer school.
Yes, and see you again 2025.
Yeah, we'll be in touch. Okay, and I'll send you the slides in a minute.
Okay, yeah, thank you.
Yeah,
okay.
have fun, everyone.
See you.
Bye-bye.